So what we've been talking about is a pretty much standard scientific method. So let's have a look at what we've been doing so far. We've saying, look, the first step in our process of investigation is to create some plot. So we've looked at really two forms of that, the histogram and the box plot. Then we've said our formal setup is always that we have a null and an alternate. And for some of these t-tests we have to have a pre-test, but our core t-test for looking at differences in the mean is always set up this. The mean of something is equal to the mean of something else, right? That's pretty much the classic setup, especially for the two sample t-test. We conduct a formal test, and our formal test relies on the p-value decision rule, which is all tied up in setting the alpha at 0.05. So we set alpha at 0.05 and apply our p-value decision rule. And then we reach a conclusion. Reject or do not reject the null. Now, pretty much up until this point, we've been saying, well, that's the end of the story. But in reality, we could be making a mistake. It could be appropriate to reject the null, or that might not be the right decision to make. So let's actually start thinking a little bit further into what's going on here. So I've got this box that I've set up here, and this is going to explain a few things, including what this alpha is. So what we've got up here, I've got the four possibilities that we can have. When you have a null hypothesis, it could be that it's true or it's false, right? So there are the two options. And once you have that, you've got a decision to either reject or not reject the null. Okay, so let's look at the first row here. Look at the true row. So if the null is true and I reject it, I've made a mistake. So what does that mean? If the null is true, there are no differences. And if I reject the null, it would mean that I'm concluding that there are differences. And we control the chance of making that kind of mistake by alpha. That's really what you've been doing. By setting alpha at 0.05, you've been saying that when the null is true, there is a 5% chance that I will incorrectly reject the null. So you think, well, that's a strange thing to be doing, but we've got to strike some balance, okay? So most of the time, in fact, 95% of the time, we would be thinking if the null is true, we would be not rejecting the null. Now, the next thing that we have down here is if the null is false. So if the null is false, that means that there are differences, okay? And so if the null is false and we do not reject the null, we have made a type of mistake. We actually call this a type 2 error, and we denote that beta. And if you think about the way that we progress science and the method of investigation, we're looking for cases where the null is false, that is, that there is some difference, there is something interesting, and that we successfully reject the null. And so that is the thing at the end there, and that's called the power of the test. So what is the chance that if the null is false, we will actually reject the null? And so I guess that's what I was leading into when we're saying, would we actually detect a difference in the previous example? How big was this power, this 1 minus beta proposition? So let's get a little bit of clarity in the language that we use here. So type 1 errors are when the null is true and we reject the null. So we'll be saying the null, there is no difference between mean plant growth, and this statement is true. So the null is true, there is no difference, and we would incorrectly concluded that there is a difference. So we'd be concluding that one fertilizer type is better than the other. So we control the chance of making that mistake by setting alpha at 0.05. So that's the setup that we have. So we have a 1 in 20 chance that we make a mistake. A 1 in 20, so if we do science a lot, we're going to make some type 1 errors. Okay, so we need to accept that, and that's why we have replication studies and all other ways of checking that we're on the right path. The next thing to talk about is a type 2 error. So a type 2 error is when the null is false and we do not reject it. So the null is false. So then what is the null? The null is that there's no difference between the two, the effectiveness of fertilizer A and fertilizer B. This statement is not true, it's false. But we don't detect there's a difference, so we would fail to reject the null. We would be concluding that we have insufficient evidence that there's a difference. So we might go, well, you know, they're both equally okay. Now, the probability of making this type of error is not fixed. So there are some factors that we can do to reduce this type of error. But let's have a look at how some of these things work. So first of all, we know that for type 1 errors, they're completely controlled by alpha. So let's have a look at how that might work. So when I set alpha at 0.05, you can see that I've got, this is my distribution of results all across here. All right, so this is the distribution for A. When I have alpha at 0.05, I do actually have a chance of drawing an observation from out in the tail that would be in the rejection zone. So remember, the middle bit here is the do not reject the null. The bit that I've shaded is the drawing a sample where we reject the null. So if I, was unlucky enough to draw a sample all the way out here, quite far from the mean, which is possible, it is possible, it's unlikely, but every now and then we will end up with a situation where we draw a sample from out here. So we would make a type 1 error. What would happen if I change alpha? Well, you can see what would happen if I change alpha. If I change alpha, it's pushing out the tail. It's increasing the do not reject zone. So if I make alpha smaller, I will reduce the chance of making a type 1 error. By making this smaller, I have reduced the chance of drawing a sample. You can see now that it's only these real bits of tails in the distribution. So there's alpha 0.05. That's how much of the tail we're looking at. Alpha at 0.01, only a very small amount. So you can see now that that sample would fall in the do not reject zone. So I would not make a type 1 error if I push the alpha rate down to 0.01. Okay, now let's flip this around and look at the type 2 errors, because it's obvious, you might think, well, why don't I just, if I want to make less type 1 errors, why not have 0.00001 as my alpha level? What will be going on? So let's have a look at type 2 errors and the role of alpha in making a type 2 error. So let's have a look at this. So here's my sample A and sample B. So the means are truly different, all right? So what I've got now is with alpha at 0.05, this little bit here is the chance of drawing a sample from B that falls in the do not reject zone of A. So, I cut off my alpha here, I cut off my alpha here, and for A, I cut off my alpha here. So there's just this little bit over here. So this would be the case where I draw a sample from B. Remember, A and B are different. This is the mean of B. This is the mean of A. These are actually different, but I've drawn a sample. There are these freak samples out here in the tail where I would fail to reject the null. Now let's see what happens when I push down alpha to 0.01. Okay, what happens is that we're pushing down out this way. Okay, so look at what happens. You're pushing out here of the reject zone for A, and you're doing the same for B. Look at those tails. So it means that as we push out A, we start eating further into the possibility of drawing samples from B that will fall in the do not reject zone of A. So this has gone down. Because this has gone down, the yellow mass has gone up. Because the yellow mass has gone up, the yellow mass is our chance of making a type 2 error. Now, as I've set this particular example up, you can see, well, you might say, well, that's a really tiny bit of yellow. Your chance of making a type 2 error is tiny. And here, it's still very small. So, should I be really concerned? Well, let's now have a look at what happens when the difference between the two samples is a little bit closer. So now the difference, so the two samples are truly different, but they're a little bit closer, and you can see what's happening with the shape of this distribution. This is my do not reject zone over here, but now these are the samples from B. This is the space. So as I've pushed them closer together, much more of the space is falling in the do not reject zone of A. So now there's quite a big chance of drawing a sample from B that falls in the do not reject zone for A. And if I was to push down alpha, so let's think about what would happen. If I push down alpha, it means that we're going to go down this curve. The black is going to go down there, and it means that this bit here is going to be added as yellow. So we're going to be adding more yellow, and look at the height. The height's rapidly increasing here. So the chance of making, if I push this down a little bit, I'm starting to really eat into the chance of drawing a sample from B that falls in the do not reject zone for A. So let's see what happens. And that's exactly what happens. We pushed this down and the total yellow area has increased quite substantially. So what have we got? We want to detect a difference. The power is the test. The power of our test is the ability to detect a difference if there's truly a difference. So we can change alpha. So instead of setting alpha at 0.01, we could increase it to 0.05, and that's increased our power. We could increase the sample size. We'll look at that. Why does increasing the sample size work? Because it decreases the distribution of the standard error of the mean, and that's going to have some benefits for us. Or we could do some structural things. So the structural thing that we've learnt about to reduce variation in the sample is with our paired t-tests. But there are other things that we could do to reduce variation. So let's have a look at how they play out. So if we change alpha, you can see that we shrink the yellow. So 1 minus the yellow, or the red error, is the power of our test. So when I increase alpha from 0.01 to 0.05, I have increased the power of my test. Of course, there's a cost to that. There's a cost that I've changed the type 1 error rate. Now, if I increase my sample size, the population, our guess of the population standard deviation is unlikely to change, but the distribution of the standard error of the mean does change. So you can see that that's much tighter. If we have a much tighter distribution, then we have increased power to detect differences if there truly are differences. And controlling variation, so the structural variation within the sample. So here the sample size is the same, but when I've controlled for variation through my experimental methods, then I've reduced the sampling variation, I have more precision, I have more ability to detect a difference if there's truly one there. So let's just go back and have a look at what we had. So remember, this is our box. Null hypothesis can be true or false. For any given null hypothesis, we can reject or do not reject. If the null is true and we do not reject, that's a good space. So we would like to have a high chance of being in there. If the null is true and we reject it, we want to have a low chance of being in there. If the null is false, we want to reject it. So we want to have power, high chance of being in this box, which is if the null is false, that means there really are differences. We want to be able to detect them. That means rejecting the null. And we want small of this. So when the null is false, we want to not rejecting it. So we have our two error types. We have type 1 errors. These are the ones the null is true and we reject the null. We want to avoid making those mistakes. It's controlled by alpha. Type 2 errors, the null is false and we don't reject it. And we want to control those, and we control those with three things: alpha, variability, data variability, and actually something that I didn't talk about really, but the size of the difference between the means that we're trying to detect. And that's an opportune time for a break.